For Chapter 5, we're going to look at nuclear chemistry. The standard chemistry that we are spending most of the semester on is where atoms are coming together and maybe sharing electrons, maybe losing electrons, gaining electrons, but the nucleus stays the same. Nuclear chemistry is different in that the particles are being emitted from the nucleus, and the nucleus itself is changing, and that changes the identity of the element that's reacting in many cases. So this is a little bit unusual, this type of chemical reaction. And it's very energetic. There's a lot of energy produced in nuclear radiation. Some types of nuclear radiation cause particles to be emitted, and then other types cause just energy to be emitted. So we have alpha, beta, and positron emission, where the nucleus of a radioactive atom, so a radioisotope, is going to emit a particle from the nucleus, and the nucleus itself is going to change. So there's a few different kinds of particles, alpha, beta, and positron, that can be emitted, and we have symbols to show what these particles are, and these symbols will become very useful in just a moment. We'll see how when we write a nuclear reaction, having this mass number, here's the mass number up as a superscript, and the atomic number as a subscript, those are very useful because that will help us keep track of what is happening in the reaction. So some isotopes of different elements are unstable, and they spontaneously emit one or more of these types of particles, or sometimes they emit just gamma radiation, so that's another type of emission. But this happens naturally. The nuclei have a ratio of protons to neutrons that makes them unstable, and so they spontaneously decay and emit these particles and energy. So the first type, alpha emission, is actually a helium nucleus. So we have this alpha particle, which is a nucleus of helium having 2 protons and 2 neutrons, giving a total mass of 4. That piece, 2 protons and 2 neutrons, is emitted from the nucleus. And the nucleus of the element, since it has fewer protons, is going to have a different atomic number and is actually going to be a different element after that. For beta emission, an electron is emitted from the nucleus, which we know that electrons are normally not found in the nucleus, but this happens when a neutron is actually changing to a proton. So we get something with 0 charge becoming something with positive charge. And so since 0 is going to positive, 0 is positive 1 plus negative 1. So a proton and an electron would have the same charge as the neutron. So if the neutron is changing to a proton, there's an electron left over, and that gets emitted from the nucleus. A positron emission is the opposite, when a proton is changing to a neutron, and then we have a positively charged electron, which is really strange. It's antimatter, which means that it's not the same as regular matter. And so that is a very strange particle. A lot of this chemistry is very strange. It's a very strange particle. It gets emitted, and since it is the opposite of matter in general, as soon as it runs into an actual electron, it will annihilate that electron and create gamma rays. So positrons do not hang around for very long. Whenever the antimatter comes into contact with actual matter, which does not take that long because matter is all around us, whenever the positron comes into contact with matter, then it is destroyed and creates gamma rays, which are energy. So some nuclei just emit gamma rays, which is a type of radiation. It's a very high energy radiation, and so when gamma rays hit other atoms, it can knock electrons off of the other atoms. So gamma rays is a very high energy. It's called ionizing radiation. Let me put that over here. So these are the different types of things that can be emitted from the nucleus. And let's see what happens to that nucleus. So we can write an equation, a chemical equation, but it's a nuclear chemical equation. To complete these equations that are showing what's happening to the nucleus, the important things are the mass numbers and the atomic numbers. Remember, the mass numbers are the superscripts and the atomic numbers are the subscripts. And those have to balance on both sides of the arrow. So this first example over here, we have one nucleus on one side of the arrow, we have a particle getting emitted, and then there is something else that results when that particle gets emitted. So this stuff on the right is the products, and the stuff on the left is the starting material or the reagents. And we have to have the mass number on the left side of the arrow add up to the mass number on the right side of the arrow. So on the left side of the arrow, here's our mass number. We have a mass of 238. We can write that over the arrow, we can make that be an equal sign, because the 238 that are on the left side of the arrow have to equal the mass numbers that are on the right side. We have one mass number of 4, and then we have a mystery. We don't know what the product is. That's what we're trying to figure out. But we have this other mystery mass number that it's going to have. So we have 4 plus, we'll just put this as a question mark. So if you use this question mark as an x, let's say, you can use algebra to solve this. We'll subtract 4 from both sides of the equation. Then on the right side of the equation, we just have the question mark alone, and we have 234 being equal to the question mark. And we can double check 234 plus 4 on this side, on the right side, is the same as 238 on the left side. We can do the same thing with the atomic numbers. So we have 92 on the left-hand side of the arrow, and we have 2 and a question mark on the right side of the arrow. We'll do the same thing, subtracting 2 from both sides of the equation, and we get that our question mark equals 90. And we put that there, we can check it. We have 2 and 90 on the right side, 92 on the left side, so those are equivalent. So we have a nucleus with a mass of 234 and an atomic number of 90. If we look on our periodic table, the element that has an atomic number of 90 has the symbol TH. It's thorium. So we have thorium-234 being the product of this alpha decay of the uranium nucleus. Let's try this same thing with the beta emission. So for our mass numbers, we have 14 on the left. We have 0 plus a question mark on the right. So our question mark has to be 14 for that to work. Let's fill in our mass number of 14. Now for the subscripts, the atomic number, we have 6 on the left, -1 plus question mark on the right. We'll solve this by adding 1 to both sides of the equation. So we get that our question mark equals 7. We can double check that. We have 6 on the left, -1 and 7 on the right. -1 and 7 add up to 6. So we have the left and the right side being equal. When we look on our periodic table, the element with atomic number 7 is nitrogen. So when carbon-14 decays through beta emission, it produces an atom of nitrogen. Let's do the same thing with a positron emission. So remember, our mass are the superscripts and our atomic numbers are the subscripts. So for the mass, we have 24 being equal to 0 plus question mark. So our question mark is actually 24. We'll put that for our mass. The atomic number, we have 13 being equal to 1 plus a question mark. So our question mark has to be 12, because 12 plus 1 equals 13. The element with atomic number 12 is magnesium. So we'll put that as our symbol. And aluminum, 24, when it undergoes positron emission, it emits a positron, and the nucleus that is left is magnesium 24. The symbol for gamma emission, this is a Greek gamma letter. It has a 0 and a 0. That's because the gamma is not really a particle, it's just an energetic ray of energy. It's a gamma energy that's being emitted. So we don't actually have a change in mass or in atomic number. That's why these are zeros. So we have 99 being equal to 0 plus 99, and we have 43 being equal to 0 plus 43. So we have not changed the identity of our element here. The only thing that's happened is that this little M has gone away. The M stands for metastable, meaning that this is a highly energetic nucleus of technetium, and so when it decays, it just becomes more stable. We have an atom of technetium that is in a high energy unstable state. It releases some energy, and then it becomes a more stable state, and it's lower in energy. So it's not going to decay anymore and release any more energy. Let's go ahead and practice an example of each of these kinds of emission on our own, and then I'll go over the answers in just a moment. Maybe pause the video for that. Also, we're going to tell what type of reaction this is. So for our mass number, we have 35 being equal to 0 plus a question mark. So our question mark is 35 for that one. And then for the atomic number, we have 16 being equal to -1 plus a question mark. So our question mark has to be equal to 17. And that gives us an atom of chlorine. The type of particle that was emitted, the E with the -1 charge, that's a regular electron. This is called a beta particle or beta emission. We can also call it beta decay. This next one over here, we have 89 as the mass number being equal to 0 plus a question mark. That means 89 is our question mark. And then we have atomic number 39 being equal to 1 plus a question mark. So this one, our question mark has to be 38. So we have something with a mass number of 89 and an atomic number of 38. 38 is actually the element strontium. The thing that was emitted here is a positively charged electron. That's a positron. So this type of reaction would be called positron emission. Over here we have 234 mass number being equal to 0 plus question mark. That means our question mark is 234. And then we have 91 being equal to 0 plus a question mark. So 91 is our question mark here. So this is one of those reactions where the only thing that's changing is that something is going from a high energy metastable state to a regular, more stable, less energetic state. But the element itself is not changing. So we have the element protactinium here, and it's still the same after this emission of gamma radiation. So we would call this type of reaction gamma emission. One last one to try, we have 210 being equal to 4 plus a question mark. This would make our question mark being equal to 206. And then we have for the atomic number 83 being equal to 2 plus a question mark. So 81 would be our question mark here. Then when we look on the periodic table, element 81, the symbol is Tl. This is actually thallium. The particle that was emitted here, this helium nucleus, is an alpha particle. So this type of reaction would be called alpha emission. It can also be called alpha decay. And those are the reactions here. So there's just a couple other types of nuclear reactions that you can have. The previous section talked about things that happen spontaneously, naturally, to radioactive isotopes. This is something, this nuclear bombardment is something that scientists can do to force nuclei of different atoms to either fuse together and become something bigger or split apart. So this is something where instead of having just one thing on the left side of the arrow, like we did before, we would have just one nucleus becoming two things. It's breaking apart all by itself. These other reactions, you'll notice we have two things as starting materials. So we have two things coming together. Scientists are forcing these two nuclei to come together. And then we have two or more products resulting from that. A lot of the pieces that we see are going to be the same. The alpha particles that we saw before, the helium nuclei, beta particles are a possibility. And then we have a couple of additional particles that we can have in these types of nuclear equations. So we can have a proton. A proton is going to be written like this because something that only has one proton is a hydrogen atom with a mass of 1. And then a neutron, we just would write it like this. It has no atomic number. It's not a proton, so it has a 0 here, but it does have 1 mass. We have a similar process here where the mass numbers on the left have to equal the mass numbers on the right. The only thing is that on the left we have more than one thing now. So on the left we have 58 plus 1 for our mass. The total over here is 59 actually. And then on the right side we have 4 plus a question mark. So we'll go ahead and add these together, that we have 59 being equal to 4 plus a question mark. And then if we subtract 4 from each side, we have just the question mark on the right, and we have 55 as the question mark. Let me go ahead and write that over here, and then you can look and double check. Does 58 plus 1 equal 4 plus 55? Yes, it does. They both equal 59. Let's try that same thing with the atomic number. I'll put it over here. We have more room. We have atomic number on the left of 28 plus 1. On the right, we have 2 plus our question mark. So we have 29 equaling 2 plus a question mark. And then that means the question mark has to be 27. We subtract 2 from both sides and we get 27 being the question mark. Then if we look here, 27 plus 2 is 29 on the right, 28 plus 1 is 29 on the left, so we have equal on both sides. That's what we need. When we look on the periodic table, element 27 is cobalt, symbol CO, and that is the answer. That is the missing piece in that particular bombardment reaction. All right, so we haven't quite gotten to chemical equations yet, so having this 4 in front of the neutron might be a little bit unfamiliar for some people. I'm going to go ahead and rewrite it. What this 4 neutrons means is that there are actually 4 of these neutrons being added together. So we have a neutron and a neutron and a neutron and a neutron. We have 4 neutrons that result from this nuclear bombardment. All right, so let's go ahead and look at our mass numbers and our atomic numbers again. So for this, we have on the left 15 plus 2, 49. And on the right, we have 1 plus 1 plus 1 plus 1. So I'm just going to write that as 4. And then we have the missing question mark here. So 15 plus 249 gives us 264. Being equal to 4 plus the question mark, that means that our question mark has to be 260. Because 4 plus 260 would give us 264. Let's go ahead and do the atomic number. I'll do it over here. We have more space. On the left, we have 7 plus 98. And on the right, we have 0 and 0 and 0 and 0. So we have 0 plus the question mark. 7 plus 98 is 105. So we have a rather large element over here. The elemental symbol is Db, that is dubnium. And that is the missing piece in that nuclear bombardment reaction. We have one last one to try. I had to erase so that I could scroll up. So the mass numbers here, we have 27 plus 4 on the left, 1 plus the question mark on the right. So this gives us 31 over here. 1 plus a question mark on the right. If we subtract 1 from both sides, we get just the question mark being equal to 30. I'll put that as the mass number. For the atomic numbers in that example, we have 13 plus 2 on the left being equal to 0 plus question mark on the right. So that means our question mark must be 15. We'll put that over here. You can always do a double check. 27 plus 4 is 31. 1 plus 30 is 31. That matches. 13 plus 2 is 15. 0 plus 15 is 15, so that matches. And then we'll find our element on the periodic table. It is phosphorus. And so phosphorus 30 is the missing piece in that bombardment reaction.